Okay, so now we'll work through a couple of examples of how you actually go about computing the gradients with respect to the parameters. So let's go ahead and just jump right into this example. If you haven't thought about it, you should probably pause, try to work through it yourself first. So we start off by looking at LReg. And this is the final regularized loss where we're trying to optimize for this particular problem. By definition, and this is sort of the base case we use for all our problems in general, LReg is going to equal 1. And what that means is the gradient of the regularized loss with respect to the value of the regularized loss is equal to 1. And that's true just by definition, because if you increase the regularized loss by a small amount, just by definition, it's increasing by that amount. So the slope is equal to 1. So that's our base case. And now so the forward pass is going through the graph in this direction. When we take gradients, we're reversing the direction of the arrows and going in the opposite direction. So you're allowed to compute the gradient of a variable once all Trojan nodes of that variable have been computed. So in particular, what that means is once we have LReg, we can compute both L bar and R bar. Let's go ahead and do that. L bar is going to equal LReg bar times how much influence L has on LReg. So we want to compute partial LReg, partial L. In this case, we have this function, this equation here. So that's going to just evaluate to 1. So we have L bar is equal to L reg bar. Okay. The next step here, we have R bar as well. So R bar is equal to L reg bar times the influence R has on L sub reg. So partial L reg, partial R. In this case, there's a scaling factor of lambda. So we just pull out a lambda here. So you can see how each of the intermediate computations, because we have actual values of lambda that we get to choose as the practitioner, we can actually compute each of these along the way. So like this is an actual numerical value corresponding to the gradient when we're given the specific inputs and parameters. One thing to note here is we could also compute T bar, but there is no need to. Because the end goal of our algorithm is try to update the parameters, in this case, W and B. And you'll notice W and B don't have any path to LReg that go through T. So in general, we also can't update the values of our data. Like we don't get to change the labels of our data. So we don't compute derivatives with respect to them. There are some cases where you might actually want to compute X bar if you're working with something like adversarial examples, but we don't do that here. Okay, so the next step along the way, let's go ahead and identify what Y bar is now. So Y bar, if we were to compute Y bar, it's going to equal Y affects L, so L bar times partial L partial Y. In this case, that equals L bar times partial L partial Y. In this case is Y minus T. So we're looking at these two equations here. Okay, let's carry on. So Z bar is equal to Y bar times partial Y partial Z. And in this case, we have y bar, which we computed from before, and partial y partial z is going to equal sigmoid prime of z. Okay. So one thing to note is that these computations look really simple when you compose them step by step, but you can also interpret it under the previous framework as well. Like z bar is asking how does L change with respect to z, right? And how L changes with respect to z is uh, L, sorry, L reg. So L reg is affected by L is affected by Y, and then Y is affected by Z. You can see that these two expressions are actually going to be exactly the same, except the way we're doing it now with this computational graph approach is we're decomposing it. So we have these recursive definitions, but each of these are numerical values. So we don't have to do all the previous work. We just store it as a single numerical value, and then we add the next value in this chain of equations. So the two formulations are the same. It's just we're computing things in a smarter way here. Okay, so now we actually can go ahead and compute the derivative with respect to the bias, which is one of the things we actually want to update. So B bar, W bar, these are the params to update with SGD. And B bar is going to equal, if we look at back of the graph, B affects Z, and we know the influence of Z from before, it's Z bar times partial Z partial B. Z, and so this second term is actually just going to equal 1 because B is linearly dependent. So we have B bar equals Z bar. And finally, for the very last term, we actually have two terms here because notice Z affects W affects Z, which affects L reg, and W also affects R. So we have to add up the influence of two different terms here. We have Z bar partial W. And this is when the fan out is greater than 1. We also have R bar partial W. So this is Z bar, partial Z partial W is equal to X. And then we have R bar, which we've computed before, and then partial R partial W is just equal to W. So that's how you go ahead and compute gradients with respect to every variable in the graph. Okay, we're going to do a second example now. Again, you probably want to pause and try to do this first. We're just going to work our way to H bar because that's where really the fan out is greater than 1. And this is an actual neural network. So when you have more complicated networks with more hidden units, the computations are all the same. We're just in effect summing over more units. So here, when we do the forward paths, you'll notice for Z and for Y, we have summations here. And these are dependent on the number of hidden units, which we get to choose as the practitioner. So we'll go ahead and work through the backpropagation equations again here. Again, the base case L bar equals 1. And now the children nodes are going to be Y bar. So let's just focus on Y1 in this case. We have Y1 bar equals L bar partial L partial Y. In this case, we have this final equation here. So we know that if we write this out, we have 1/2 y1 minus t1 squared plus 1/2 y2 minus t2 squared. So if we're taking the partial derivative with respect to y1, we just get something from this first term here. So we have L bar y1 minus t1. Okay. So actually, once we have y1, we can actually compute the weights and biases because they don't have any other dependencies. So for instance, we can look at W11 2 bar. And that's going to equal y1 bar times partial y1 partial W112, right? And in this case, because y is a linear function of the w's, it's actually just going to be exactly equal to h1. Okay, so here the superscripts over the weights and biases correspond to which hidden layer they're part of. So we're using W2 and B2 to denote like the connections between the hidden layer and the outputs. And similarly, we can also do the same thing for the bias. So bias 1 is equal to y1 bar partial y1. And this is actually just equal to y1 bar because the bias is, there's no constant in front of the bias. Yeah, so I noticed above that I missed the y1 bar with w11. Okay, cool. So that's y1. The calculations for h1 are for y2 are going to be very similar, but the really tricky thing, the most tricky thing here is probably finding out what h1 bar is, because h1 affects both y1 and y2. So in general, we actually need a summation here because h1 affects both y1 and y2. So we're going to sum over I and figure out what yi bar is, and also partial yi partial h1. Okay. So keep the summation yi bar. And how does y depend on h? How does y sub I depend on h sub 1? Well, it's actually going to be exactly equal to the weight factor here. So it's W 1 I 2 because we're focusing on H sub 1. In general, if we're focusing on H sub K, we're going to replace this with W. Let's cut. Okay, so that's how you work through the derivatives of a neural network in general. Once you have these H's, you can keep going back through the graph. You can find Z and then the W's and the B's, which come from Z. And the full list of how you compute each of these is recorded on the lecture slides. One thing to note is if you're actually implementing this in practice, you don't want to do a for loop to do the summation. You can actually, because it's a product of a bunch of different numbers which are conveniently stored in vectors, you can vectorize all of these operations as either matrix vector products or sometimes element-wise products between different vectors. So we show how you can vectorize everything on the following slide. I guess the key thing to note for implementation purposes is the shapes match. So what I mean by that is if you were to look at W superscript 2, the dimensions of W superscript 2 bar should be the same as the dimensions of W superscript 2. So if you're implementing it and your shapes match 90% of the time or more, it's probably right, but you should also check that each of the gradients actually match. All right, so that's the backpropagation algorithm. And the really amazing thing about this algorithm is that even if you have a neural network with hundreds of millions of parameters and different types of layers, you can always apply this fundamental algorithm and it gets you your gradients in a really efficient way. So if you were to contrast it with a finite difference-based approach, which we've previously studied, if you were to take finite differences, you'd have to change, if you have a bunch of different variables, x1, x2, all the way to maybe x sub I to xn, you would have to change one of these variables by a small amount and compute this function evaluation again to just estimate the partial derivative with respect to one single element. Then that becomes tedious and it's not quite numerically correct. In contrast, if you do a rough back of the envelope calculation on how expensive our backpropagation algorithm is, it's roughly 2 times more expensive than the cost of a forward pass. And that's because for each weight, when you're going forward through the graph, you do one multiply to the previous layer's input. When you're doing backpropagation, the weight shows up twice because you need to compute the derivative with respect to the weight, which has a multiply, and then the previous hidden layer also depends on the weight, so there's another add multiply operation. So roughly you can say one backward pass is as expensive as 2 forward passes, and that's really efficient. Like it's saying a forward pass is a sequence of composed functions, and sort of with twice the cost, you can compute gradients. And that's really the magic that makes modern neural networks train so efficiently. So you can also, I guess, express costs in terms of the number of units of a layer. So what that means is if there's, let's say, n units in one layer, m units in the next layer, the number of add multiplies, just because we have a matrix multiply, is n times m. And then you have to scale linearly with the number of layers as well. So variance of gradient descent is actually used to train the vast majority of neural networks today. The one additional note that's really important to mention on the slide is you need to be careful with neural net initialization. So your initial neural network, you shouldn't set all the weights equal to 0. And that's because if you do that, the gradients with respect to each of the variables in a given layer are going to be exactly the same because of the symmetry. And each step of gradient descent is going to maintain this property that all the weights in the layer are exactly the same numerical value. So in effect, you only have one hidden unit in each layer, and that loses all the benefits of expressivity that we want from neural networks. So in practice, what we usually do is we set the initialization of the neural network to be small weights, usually sampled from a Gaussian distribution. And one other note is even though backprop and neural networks are sort of motivated by the brain, it's probably not what the brain is actually doing, but I guess in practice we get really good results. Okay, finally, you can practice actually trying to implement this sort of approach in an auto differentiation framework. I think it's a really good exercise to try to implement backpropagation in something simpler like in NumPy, just to make sure you understand how the gradient computations work. And it's a cool exercise to see that training MNIST for digit classification, you can get 97, 98% accuracy using a neural network key coda from scratch. Eventually, when you're doing work later on, you'll be using various different auto differentiation libraries, which help you compute gradients. So for instance, in PyTorch, once you define your loss, you can call loss.backward, and that gets you the gradients with respect to the previous variables. And there's other frameworks out there, such as TensorFlow and JAX. But the nice thing about this class is if things are broken, you now have the conceptual understanding to sort of debug why things are breaking. So in later classes like CSC413, you'll investigate more how auto differentiation works and apply it to more complex neural networks.